Welcome, everyone. So it's a great pleasure to see everyone here. So this is a joint event with the Department of Statistics, Mathematics, and the School of Computer Science and Engineering, CSE. So I also want to thank Jen Chen and Ed Lazowska for helping organizing this. So we have the great pleasure of having Persi Diaconis with us today. So Persi is the Mary V. Sansari Professor of Statistics and Mathematics at Stanford University. He's working on probability, combinatorics, and group theory with a focus on applications to statistics and scientific computing. A specialty is rates of convergence of Markov chains, and he's interested in trying to adapt the many mathematical developments to say something useful to practitioners in large real-world simulations. But of course, Persi doesn't need a lot of introductions, so this is more the official template that I'm reading here. And he's also known for being not just a world-class probabilist and mathematician, but also a magician. So without further ado, I'm going to pass to Persi, and I hope you all enjoyed the talk, and we're going to have refreshments later after the talk. So thank you again for coming, Persi.
Thank you. Thank you, and good afternoon. This is a talk called the Value and Pitfalls of Proof. And I'm a mathematically inclined statistician who likes to prove theorems, and my fields have gone away from that, and with good reason. I often hear people say, why are you bothering to prove things? We can just check it on the computer and see the answer for the n's that matter, and your theorems have error terms and so forth, and it really has taken over, and it's perfectly okay with me, but there is still some value of proof and various projections, and I want to talk to you about that. The issue is that the computer lies sometimes, and that is, you can see lots and lots of output, and it's meaningless. And I've collected examples. It's hard to do because in order to collect a real messy example, you have to know what the right answer is, and that's a lot of work, and maybe hard to do. And I've tried to write some of the key examples that come from physics and social sciences in the handout, and I hope I get to them. But when I talk about examples, I find that it's as if I'm making fun of people, and I don't want to do that. So what I'm going to do is make fun of myself. I want to tell you about, with some care, about a problem that where I had computational issues, and thinking and proving were helpful. And it starts colorfully enough with a card guessing experiment. And so a standard experiment that's been repeated millions of times, literally millions of times, where people try to see if other people can read each other's mind. I'm a skeptic, don't get nervous. And the experiment uses a deck of ESP cards, and these have symbols on them. There are 5 different symbols. The symbols are a circle, plus 3 wavy lines, a square, and a star, each repeated 5 times. Equals 25 cards. And a standard experiment is the deck is shuffled up, and no cheating, it's actually shuffled, and an ascending subject, that'll be me, looks at the cards one at a time, concentrates on them, and tries to send it to a receiving subject, here Carlos, and the receiving subject guesses at the card, and then we go through the cards one at a time, next card, and as I said, that experiment was repeated millions of times. And one thing that I was interested in was the following. The way they did the experiment involved feedback, because they're supposing there was something there. You want to learn. And so the way the experiment worked is the following way. The cards are shuffled. Carlos guesses at a card. And if he says star, I see it. And he's right. I say, hey, that's great. You're right. And I look at the next card and he guesses square, and I say, nope, and I don't tell him what it is. So the feedback was yes, no feedback. Everybody with me? And so there's some information there. So this is with, so yes, no feedback. And just to help you calibrate, there are 25 cards, each card repeated 5 times. So your chance of being right on any guess, if you just guess at random, is 1 in 5. And then you have 25 shots at it. And so if you don't have any ESP or any talent at all, you expect to get 5 cards right going through the deck, a fifth times 25 being 5. And surely the feedback could help. And we wanted to understand how the feedback helped and how a subject who was trying to get as high a score as they could use the feedback. And I was working at Bell Labs at the time that had a big computing staff, and the idea was the same as the idea that's used in programs to try to get the computer to play poker or any game, solitaire, any game in which there are unknowns, was to try to find strategies which would get a high score. And so roughly speaking, we had some, well, first thing first. With 25 cards, using backward induction and 20 hours of computing, you can figure out what the optimal strategy is. So by pretty heavy computing, the optimal gets 6.63 right. So more than 5, a little bit more than 5. And but the optimal strategy is extremely complicated. Nobody has any idea what it is. It's stored on some enormous set of files on a computer, and we don't know what it's doing, just like all other machine learning programs. And our object was to try to get a humanly usable strategy by having some parameters. If a card is right, well, it's eliminated, so that. But what do you do when cards are wrong as you go through the deck? How should you do that? And we had rules which were with some parameters in them, and then we would try it a lot, and then use something like gradient descent to try to get a high score by wiggling the weights, just the same way that we do it today. And in one thing before I get to the main point is that I was sure that the greedy strategy, that is, at each stage, if you're told as we're going through the deck, right, wrong, 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 right, right, you can figure out what's the chance that the next card is one of the 5 symbols. That's a doable calculation. And why not just choose the most probable card for the next guess? And I was so sure that that was right, I bet $50, and I lost the bet. The greedy strategy isn't optimal. There's a trade-off between information and getting a high score, and there's a trade-off, and just greedy isn't optimal. Now, in order to do this, this is one special case. There was a suite of problems of this sort, different counts, different numbers of cards, different strategies, different setups, different amounts of feedback, and we were studying them, and the computer ran, I think the CPU time was 18 hours, and it was 2 days of running and stuff like that on big machines, and the data came back, and something was wrong. Now, what does that mean, something is wrong? Well, you look and something looks funny, and certain things that should be monotone weren't monotone, and something was wrong. And so then what do? Well, you start looking at the code, and you talk to the programmers. There was a team of programmers, and let me explain this part. In order to do simulations of this sort, you need to generate a lot of random permutations, a lot of random arrangements of the deck in a deck of cards. And how do you generate a random permutation on a computer, say for 52 cards? And you might think, well, just pick a random number and associate. Well, 52 factorial is 10 to the 68th, so that doesn't work. But here's the standard algorithm for generating a random permutation on a computer. Let's suppose I have 52 cards. Here they are, and they're in order, or in memory registers, 1 up to 52. Get your random number generator to generate an integer between 1 and 52, say 17, and swap 1 and 17. And then get it to generate a random number between 2 and 52, say 5, and swap 5 and 2. And then between 3 and 52, maybe 3, it's allowed, and then you do nothing, leaving 3 there. You have to do that. And you keep going. Now, it's easy to do, easy to program, and obviously that generates a random permutation because any card can be on top, and whatever card is there, any other card from the remaining can be next, and that's the algorithm for generating a random permutation. So after 2 days of looking at code and not being able to find anything wrong, I said to the head programmer, I'm lost, but how did you generate your random permutations? And she said, oh, you said that fussy thing, random with 1, random with 2. I made it more random. I switched random with random. I said, you have to redo the simulations. That's not right. She said, but I did 100 random transpositions. That has to be enough to mix up 52 cards. And I said, I'm sorry, it's not right, and I didn't really know but I just didn't feel right. It wasn't the right algorithm. And she went to her boss, and he went to his boss, and his boss came down and screamed at me, 100 random transpositions, you mathematicians are crazy. It has to be enough to mix up. That can't be the problem. So I really wanted to know the answer to the question, how many random transpositions does it take to mix up 52 cards? Okay, everybody with me? Okay, all right. So, and so that was a math problem now. And let me. I have a list of the stories to tell, and that's one of them. Okay, so. So let me say that a little bit as a math problem. So I'll be working on what we call SN, which is all n factorial arrangements of a deck of cards. N factorial arrangements. And random transpositions in English, you have a row of cards face down. You pick a card at random with your left hand, you pick a card at random with your right hand, and you switch them. And you do that a lot. And obviously, the cards get all mixed up. Okay, so how do we make math out of that? Well, we say the chance of one switch, Q of permutation is equal to, it's 2 over n squared if sigma is a transposition, ij, and it's equal to 1 over n if sigma is equal to the identity. That is, you have to allow your left hand and your right hand to be equal, otherwise after an even number of switches you'd be at an even permutation, and that's not random, that never gets random. So this is a mathematical model. This is a mathematical description of switch a pair of cards at random. And do it twice, q star q of sigma, the chance of being at sigma after 2 switches, is equal to the sum over eta of q of eta times q of sigma eta inverse. So in order to get to sigma after 2 switches, you have to do something, your first step, and then choose the permutation that gets you to sigma. The second step, and q star k, is the chance of being at a permutation sigma after k switches. So there I'm writing it down, and the uniform distribution, u of sigma, is 1 over n factorial, all permutations being equally likely. And the first theorem in the subject, Poincaré, 1890, if you q star k of sigma goes to u of sigma, that is, you all know that if you shuffle a deck of cards a lot, they get all mixed up. Sure, I mean, but if you switch the cards a lot, they get all mixed up. And I needed to know how fast. So question, how fast? When n is 52, if k is 100, is that enough to make the distribution close to uniform? So let's write that down as math. The distance between shuffling k times and the uniform distribution is just equal to the maximum over all questions A. I'll interpret this in a second, of q star k of A minus u of A. So what that means is the following. So A is a set of permutations, like the set of all arrangements of a deck of cards where the ace of spades is in the top half. And this is, what's the chance that if you shuffle k times, your deck of cards is in this set of arrangements? This is, what's the chance if you shuffle perfectly, not perfectly, but if you shuffle, if the deck is random, of u of A, you take the difference between those two numbers and you take the maximum. So if this is small, say less than 1 in 1,000, it means for any job, for any test question A, whatever you want to do with your permutations, the deck is the deck is well shuffled. And so here's what a theorem in the subject looks like. Theorem, and this is joint work with Shashahani. Let k, the number of shuffles, be 1/2 n log n plus c. C, say, bigger than 0. So I'll explain in a second. Then the distance to uniform is less than or equal to 2 e to the minus c. So let me try to explain that. You know n, the deck size, n is 52. So k is how many times you're shuffling, and if you know n and if you know k, that tells you what c is, and that c is the same as this c. So this says if you shuffle cards 1/2 n log n plus a little bit, then you're exponentially close to being mixed up. And when n is 52, 1/2 n log n is about 100. It's 103 or so. And so that's, you know, n is 52. Log n is about 4.5 times 1/2. It's about 100. And so there's a lower bound which says that this number, you have to do at least this number, and you have to do this many suffice. So suppose I want the right-hand side. Say want the right-hand side less than or equal to 1 in 1,000, or you get to put in whatever number you want. Then if you want this less than or equal to 1 in 1,000, you can solve for C. And this says that 460 or so, 68, suffice. So I want to stop for a second. There's some math work to do to prove a theorem like this. And it gives a pretty good answer in the sense that it's, 52 factorial is, as I said, 10 to the 68th. Maybe you have to shuffle that many times. No, it's between 100 and 400 or 500. But it doesn't tell me whether I won the argument with the Bell Labs brass. It doesn't really tell me how many times suffice. But still, it's better than most of us know when we think about our algorithms. In the course of proving this, we figured out what was wrong with shuffling. So think about that for a second. Here are the cards in order, 1, 2, up to 52. And suppose you don't switch enough times. Why wouldn't it be random? Well, if you don't switch enough times, there will be some cards that you didn't touch. Right? And those cards are fixed points of the permutation. And we know from elementary probability that a random permutation should have 1, 2, or 3 fixed points. 0 fixed points has chance 1 over e, about a third of having no fixed points if the permutation was random. And so if you don't shuffle enough, there are too many cards which were in the same position they started with. And our algorithms, the card guessing algorithms, were clever enough that they glommed onto that, and the scores were higher than they should have been because they used the fact that the cards weren't well shuffled. They figured that out. And that, of course, is a problem in all kinds of machine learning problems. The algorithms will pick up on anything. I want to say a sentence about the math behind this kind of thing, just because you'll see why in a second. So, but this is where I got to with a fair amount of work, and I understood why the computation was wrong. And then this happened months afterward, and actually one of the co-authors on the paper was the head of the math group at Bell Labs, and he said, do the simulations again. And so they did the simulations again, and the answers changed, and they made sense. I'll tell you a bottom line of that. Remember, I said the optimal strategy, the best you could possibly do on average, was getting 6.63. And the strategy, the rule came out to be that 2.5 wrongs was about equivalent to 1 right. And a human can do that if you're keeping score of rights and wrongs on each of your guesses. And our strategy did about 6.61. So there was a humanly understandable strategy which did close to the optimal, and certainly close enough for practical work. One board of math, well, we'll see how honest I am about that. We used Fourier analysis on the permutation group. Everybody here probably knows that every color can be made up out of basic colors by combining them. Every tone can be made up out of pure tones. Every signal can be expanded into sines and cosines, and that is the world and set of techniques of Fourier analysis. Fourier analysis is Fourier analysis for the real numbers. And every group has its own sines and cosines. Every group has its own Fourier analysis, and that's called representation theory. And we needed the representation theory for the symmetric group, for the group of permutations, and that's well understood. So a representation is assigns to permutations matrices, D by D matrices, if it's a D-dimensional. So with the property that the matrix that you assign to the product of two permutations is the product of the two matrices. And so everybody probably here knows the permutation matrices, and that's a representation, the n-dimensional representation of the permutation group. And it is a fact that if you multiply two permutations and take their permutation matrix, that's the same as having the two permutation matrices and multiplying them. So a permutation, a representation assigns matrices to permutations. In this way, these are invertible matrices. And then the Fourier transform, I'll write it up here. If I have a probability measure like that one, Q hat at rho, the Fourier transform at rho is the sum of Q of sigma, rho of sigma. And here you add up the matrices weighted by the different probabilities. And as usual, Fourier transform takes convolution into product. So Q star Q hat at rho is equal to Q hat at rho squared. So it converts convolution into product, and the same for Kth powers. And so, and the Fourier transform of the uniform distribution, U hat at rho, is equal to, well, 0, unless rho is the trivial representation, and if rho has to be what's called irreducible, if rho is irreducible. Okay, happy to tell you what that means if you want. And so proving this theorem, studying repeated convolution, I had to show that the Fourier transform, the Kth power of the matrix, tended to 0 as K went to infinity. That's translating the question of showing that repeated convolutions tend to uniform into Fourier analysis. Now, these are still very big matrices, and then a miracle occurred. It turns out, so miracle, here it is. Q hat at rho, instead of being a big, huge matrix, was in fact a constant times the identity, where the constant is equal to the character of the representation at a transposition over the dimension of the representation. And this is these are the characters. And so in order to study the convergence of repeated convolution to 0, I just had numbers to keep track of. And then classical theory tells me what these numbers are and these numbers are, and then a month of hard analysis, and you have your theorem. And that was that theorem. Well, I said it was going to be one board, and I took 2 boards. But so that was some of the math that was involved, and let us get to the answer. Okay, so this talk is called, or in my mind anyway, it's called The Benefits of Proof, because I like proof, and what good is it? So, okay, I worked hard, and I figured out what was wrong with this code. There were a lot of numbers on the page, and all of the numbers were wrong, and we were able to understand that, and then prove theorems, and go back and calibrate. And what are some benefits of having done this work? Benefits. Well, from understanding this method of mixing, I could understand almost any other method of mixing, any other mixing problem that had been suggested. So there's something called comparison theory, and I'll try to explain comparison theory. Comparison theory lets us bootstrap this analysis to do most shuffles, and let me explain that, most shuffles. So I'm not the only one who studies shuffling. Lots of people in probability are interested in that question. Emil Borel, the father of the law of large numbers, and Paul Levy, and many other people studied various shuffles, which are very different from random switches. For example, take the top card off and put it in at random, and just do that a lot. Okay? That's a way of shuffling, and if you do that a lot, the cards will get all mixed up. How many shuffles does it take? Borel and Levy said, pick a random packet of the cards and put them on top. Or this way of shuffling, the klutzy way of shuffling that people do. How many of those does it take? The answer is n squared log n. It's about 10,000 when n is 52. So it's a poor way of shuffling, even though it's the second most popular. So dozens of ways of shuffling that people had studied and not been able to prove anything about. I could get theorems of this sort, sharp results, upper and lower bounds that matched, using the fact that I knew this one shuffle, and that subject is called comparison theory, and I put a reference down in the handout in case that's the kind of thing that interests you, and you can take a look. So let's see. That's one benefit of proving things. There is the other part of the argument, which is the problems of proof, because you could say, well, I did all this hard work, I used some nice math, it's great. Then you should think, yeah, but I didn't actually solve the problem. I mean, I don't know whether, I know that 100 shuffles wasn't enough, but I don't know, how many shuffles does it take? So often theorems are asymptotic theorems, and people usually don't keep as good track of the constants as we were able to here, and actually the results are often useless and that's, I think, what practitioners feel. Well, people prove these theorems, and they have nothing to do with actual sample sizes and underlying assumptions that run during the day. So that's one of the pitfalls of proof, is that you can trick yourself into thinking you've actually made progress when in fact you just managed to prove a theorem, and that's nice, but it's not solving the actual problem. So what about the real problem? That is, the one I started with, and that I got into arguments about. What's the answer? Well, I now know kind of roughly what the answer is. It's between 100 and 400 or 500, and so an idea is to go back and try to study it by simulation. So idea, fix some number of shuffles k, fix k, say 100, 120, 130, fix some number of k, simulate shuffling k times, generate n repetitions, call them sigma 1, sigma 2, just say k was 100. Do 100 switches, record the order. Do another 100 switches, record the order, and do that I'm from Stanford, I'll use B. Do that 10,000 times. And so that gets you a sample of permutations. And then you can try to test if these guys are from the uniform. Now, let me try to address that for a second. Suppose n is 52, and b is 10,000. So I have 10 to the 68th boxes. That's all possible permutations. And I'm dropping 10,000 balls into 10 to the 68th boxes. And I want to test if they're uniform. You got to be kidding. I mean, think about it. All the permutations that you generate are going to be different, and you've got 10,000 balls dropped into 10 to the 68th boxes, and you want to test if they're uniform. You can't do that problem. I mean, without thinking. Naive asymptotic theory says the box counts are all going to be 1, and they just are the same. And, so of course if all the balls dropped in the same box, then you say that's not right. So we have to think. Okay, it's good. Every once in a while, it's good. So thinking. So why wouldn't permutations be random? Well, anybody, if they started thinking about it, could think of certain features of the permutation. For example, the number of fixed points, or is the original top card still back on top? Or pick some distance between permutations, a metric, and look at the distance of your permutation to the starting arrangement, and that would get you 10,000 numbers, and then you could see whether they looked the way they should. I mean, so if you picked features of a permutation, then that's good. I mean, that helps, and you have to do something like that. You have to, in classical language, you have to say what alternatives you want power against, but I like to say you have to think. And so suppose I had various features, T1, which is the number of fixed points, T2, which is the top card, the label of the top card. T3 is the label of the bottom card, the bottom, etc. TK, some features of a permutation which make sense is equal to the distance of sigma to the original starting order. Then we could build those into a standard model. So you have to learn how to clean these boards. Well, it won't be so bad. Maybe I'll use another color. Then keep going until the end of this board. You could make a probability model on permutations. P sub theta of sigma is equal to e to the sum of theta I t I of sigma, I equals 1 to k, and then there's a normalizing constant. Which makes it add up to 1. So this puts a non-uniform distribution on permutations, which is regulated by these features. And the null hypothesis is theta equals 0. Test if theta equals 0. And that's a standard-ish problem. This is called an exponential family. And testing whether a parameter in an exponential family is 0 or not is a standard thing to do. Now, given that I'm building these features in, I think of that as being a Bayesian about the problem. What do I think if the thing isn't uniform? What is it likely to be? And so I wanted to use I wanted a Bayes test, what's called a Bayes test. and you could do other things too. But a Bayes test, you put a prior distribution on theta, pi of theta, prior on theta, and then you can ask, you can test H naught that theta is uniform versus H1. It's not uniform. And the way the standard test goes is you compute the probability of H naught given the data. You have the data, and divided by the probability of H1 given the data. And if that ratio is big, then you say H naught is true, that the cards are well mixed, and if it's small, you say H naught isn't true. And using Bayes' theorem, this is the probability of the data given H naught divided by the probability of the data given H1 times probability of H naught, the prior probability. So this is Bayes' theorem, and often we take this ratio to just be 1 a priori, but you can take it to be whatever you like. And this numerator is easy to calculate, and that is if the cards are well mixed, what's the probability of seeing the data? Well, if they're all distinct, the chance is the chance is 1 over 52 factorial raised to the b power. I mean but other, we can do this calculation. This calculation is troublesome, and it's troublesome even if you think you know something. That is, many people know that you can simulate from probability distributions if you don't know the normalizing constant. This is worse. This is the problem of doubly intractable distributions. Doubly intractable. Try to explain. The calculation you have to do is you have to do. Suppose we want to simulate from what's the sorry, I got Bayes' theorem backwards. That's well. No, this is okay. I mean, this is okay. But I'm gonna do this anyway. This calculation, you want to simulate from this. So the simulate from simulate thetas. Simulate thetas, the parameters from p theta e to the theta dot, and it would be the sufficient statistics, but t, all right, but divided by z of theta. And the problem is you don't know z of theta. Problem, you don't know z of theta. Z of theta is an unknowable sum. It's a sum over n factorial permutations, and you don't know it. And so people try to deal with that in various ways, and there's a large literature. The way we worked with it, and it seems to work very well, is a new algorithm, newish algorithm called the exchange algorithm. Change algorithm, and I'm not going to explain that, but I gave a reference, which is a way for sampling from distributions of this type, because you're sampling in theta and you really don't know z of theta, and so you have to deal with that. And there's this clever new algorithm. I'll just tell you the answers and what came out of this. So here's what these Bayes factors were. This is k, the number of shuffles, and I tried 100, 120, 140, 160, and here's 180. I skipped one, and the Bayes factors, this was 0, this was 0.051, this was 5.6, this was 18.6, and this was infinity. I mean, it was a huge numbers, and 170 was also reasonable. I mean, not so out of. So there was a sharp cutoff. That is, the chance of the null hypothesis being true went to infinite odds against any alternative when you passed 180 shuffles. And so this and other arguments made, for me, convincing proof that the answer is 180. And I was happy to find that. So let me say where we are in this list of examples. I tried to tell you in some detail an example of a large simulation where the computer programming was off, and was off for various reasons, but the main one was an algorithm wasn't run long enough. We were able to do the math of it and explain why it was off and convince people to redo it. And then the math had legs of its own and leads to being able to solve all kinds of other problems. Okay, and in the end, but I had to come back and use the computer in order to get useful answers. But the math narrowed the range that I needed to simulate in to something that was reasonable. I knew kind of what the answer was, and then I could use Markov chain Monte Carlo. Okay, so that's a typical scenario of the benefit and pitfalls, I think, of proof. Now, I want to talk a little bit about some of the examples in the handout, and let me switch gears. So wait a second. New talk starting. Okay, you're asleep. I did some math, statistics. New talk stories and new talk starting. Okay, so. This example comes from simulations in physics, and the three most widely used simulation algorithms all come from physics. They're the Metropolis algorithm, Glauber dynamics, we call it the Gibbs sampler, and molecular dynamics. And they were all introduced by physicists and chemists in order to solve one problem. What's the problem that they were interested in? Suppose you have n disks. I'll take 2 dimensions. Disks of radius h, say h, in a box. And you want to put them in. So they're little balls, which are disjoint and fit in the box. That don't stick out. So, of course, a configuration of disks in a box is determined by the centers of the disk, and there's some region of centers which don't overlap and which fit in the box, and that's called the configuration space. And the configuration space, if there are n disks, each center is 2 dimensions, so it's a 2n-dimensional part of Euclidean space, and it's compact. as a space, and so it inherits a uniform distribution, just the usual Lebesgue measure, restricted length, area. So we want to put disks in at random according to the uniform distribution in this box. And why would people want to do that and try so hard to do that? Well, it has to do with phase diagrams, and everybody's seen those in high school. I guess this is temperature, and this is pressure, and this is phase diagrams look something like this, there's, for many atoms or molecules, there's a triple point, and then there's, this is a liquid solid interface, and then this is, if the temperature is very high, it'll be gas, and if the pressure is very high, it'll be solid. And Kirkwood and many other physicists noticed that many molecules have phase diagrams that look like this. And there has to be a reason. It can't just be the details of the attraction between the electrons. And Kirkwood hypothesized that the reason that there was a phase transition, that there were phase transitions and that the diagrams looked like this, were that was repulsion between atoms. That is, two atoms can't be at the same place. And so he said, let's take the simplest possible model that captures that, which is energy of the configuration is infinite if they're touching, and zero otherwise, and then e to the minus beta h, the normalized, is the uniform distribution over all configurations if they're among all non-touching configurations. And so he hypothesized that this model would have phase transitions. And it does, seems to, not that we can prove that, but in 2 dimensions, there's a phase transition at 0.71. So let me try to explain that. The only one parameter in the problem is the amount of area that the disks cover in the box. Everything else doesn't matter. And so if the density of the disks is bigger than 0.71, the disks look as if they're on a lattice. They're all neatly lined up. If the density is less than 0.71, 0.705, the disks look random. And experiments show that it seems to be true, simulations. So how do you simulate? Well, there are these 3 algorithms. Let me just say them briefly. You want to put disks at random in the box. So you put them in some way, and then Metropolis is, you pick a disk at random, you try to move it a little bit. If it fits, good. If it doesn't fit, stay where you are and pick another disk. So you just wiggle around a little bit, and that's the Metropolis algorithm. Glauber dynamics is you pick a disk at random, you pick a place at random, and you try to move the disk to the place where it can move. Molecular dynamics, you give each disk a velocity, and then you let Newton's laws, you let the disks move around and they bump off each other, and people try to simulate that way. And millions of hours of CPU time has been used simulating hard disks. And so people use it, really use it. And then, so I was at the meeting where Werner Krauss made an announcement, and physicists aren't polite. You people are pretty polite. But, if you say something, they don't like, how could you say that? Werner Krauss got up, he's head of physics in ENS, Paris, and he said, you guys have been simulating for 60 years, all your simulations are wrong. And he had a different algorithm, and at first people just exploded at him, but after it was a 2-day meeting, and they said, well, we'll go and try it, and it seems as if he was right. That is, think about simulating at anywhere near 70%. You try to move it a little bit, you don't move, you just stay where you are, and you wind up just rejecting your possible moves. They just weren't simulating long enough. That didn't stop them from writing papers. as it doesn't stop us from writing papers, sorry, but that is, and for me it's like people looking up at the stars and seeing animals. You know, oh, there's a dog. You know, you can look at the simulations and make up stories, and that's what they were doing. And contradictory stories, wrong stories, the standard picture that emerged from years of simulation was just wrong. Okay, so I wrote down references. I'm just telling you that. We can discuss forever, but that's an hour's talk to try to justify that and explain that. You can look if you want to see, but people seem to have come to that conclusion. And if smart, thoughtful, hardworking scientists can get it wrong for year after year, you know, that's an example of where the computer lies. Okay, where it's not that we can prove much, but we can prove some things, and so that's an example. I see our time is essentially over, and so I should stop. But I just want to point to my last example, which was from the social sciences, which tries to understand how people come to have a common language, or how people become friends, or that kind of thing. And all of it's done by simulation. And I document, if you look up the references, I document extensive simulations which were wrong because math eventually showed that the simulations converged at rate 1 over square root of log n. And so somebody, I was there for the argument, somebody said, I simulated 50,000 times. And the guy said, your thing converges like 1 over root log n. It's not enough, and your conclusions are wrong. And my friend Brian Skirms had written half a book based on wrong simulations, interpreting them, making up stories about how we interact, and it was all wrong. Okay, so lots of people get it wrong too, and math can be a useful antidote, but math can take itself too seriously, and math can forget that there's the real world out there. And I'll end with my favorite example. One of the deepest things that's been done in probability is the distribution of the length of the longest increasing subsequence in a random permutation. And if you pick a permutation at random with n things and look at the longest increasing subsequence, it's around 2 root n if you subtract off 2 root n and divide by n to the 1/6. It has a limit called the Tracy-Whittem distribution. How large does n have to be so that approximation, one of the great Bike-Dief-Johansen theorem, a great piece of mathematics, so how large does n have to be so that that's useful? Turns out n has to be around 10 to the 9th. 10 to the 9th is bigger than 52. Okay. On the other hand, if you have an n by n matrix, Hermitian matrix, and look at its largest eigenvalue, GUE, if you know what that means, the largest eigenvalue is around 2 root n, and if you subtract that off and divide by n to the 1/6, that also has a Tracy-Whittem distribution. That works when n is 15. So there are good limit theorems and bad limit theorems. And mathematicians don't seem to care much about that. Okay, or it's hard work to try. The 10 to the 9th is from simulations. We can't prove very much about that. So what I hope to illustrate in this talk was that the computer can lie, math can help, but math shouldn't take itself too seriously. I hope I didn't either. Thank you.
Thanks so much, Persi. We have time for questions, even though I think we're out of time.
And complaints are okay.
Yeah. All right, so let's get started with the questions.
Hi, Sarah.
Okay, lovely talk, as always. And maybe you were getting at this at the end of the talk, but I was wondering, do you have a list in your head of what are the top 10 best permutation statistics to test uniformity among a collection of permutations?
The question is, do I have a list in my head of what are the top 10 permutation statistics? It depends on the shuffling mechanism. So you can't get away from thinking. So in the case I did with random transpositions, we know it's theorem of Oded Schramm, our local hero, that the main thing that's wrong is the number of fixed points, and that's all you need. You didn't need a lot of other things. In the case of the work I did with Shomik Pal, smushing cards around on the table, well, if you don't smush enough, why wouldn't they be random? Well, maybe they're cards which were originally together that are still together, or the original top card is back on top of the original bottom card, is, that kind of thing. So it depends on the mechanism, and so I don't have a closed form answer, nor do I think I should have one. I think we shouldn't use one. I think we should think. I mean, I know people think we have to automate everything, but I think that way lies madness.
Thanks.
It was so clear this.
Don't be shy.
It's okay.
Well, I do have a question. So you mentioned sharpness at some point. So I'm not very familiar with this work, but could you elaborate on the sharpness claims of the bounds?
Oh, well, thank you. We didn't prepare that. So the theorem that I stated, you might think if you look at how mixed up you are. You might think, well, it just, you start out not being very mixed, and as you as you shuffle more and more, it just, the measure of distance to uniformity goes to 0, and that's true, but it's misleading. I didn't do that, and I have a good pen, or I have a lot of good pens, and watch out, gang. Well, I have a lot of good pens. Well, okay. What the total variation distance looks like, it looks like this, and this breakpoint is at 1/2 n log n, and it goes to 0 exponentially fast after that, and it actually goes to 1 doubly exponentially fast in C, and we know the shape of this. We know that's Lucas Tessier's beautiful result using character theory and hard work and good ideas. And so I have, finite upper and lower bounds. I said one, e to the minus twice e to the minus 2c. There's a lower bound like that. They weren't so close together, and then we can sharpen those and get them better. And I just 2 days ago I got a paper from Vicious Chain with a very precise bound in this random transpositions problem. We wrote that paper 45 years ago, and people are still thinking about it. In the references, I was shocked. Some of our physicists who work on black holes came to me and said, your paper about random transpositions? I said, yeah. And they said, well, we're using it in blah, 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 blah. And I put the reference in. So all that hard work I did seems to illuminate a question about black holes. And I can't say another word. I said more than I know about, but I did put a reference in. So we got very, very sharp analysis because we could do Fourier analysis. And we're, lucky, hard work. We often can't do that. And I know David Dunson, who's a friend who does a lot of simulations, where is Carlos? You're there someplace. There you are. I mean, people who actually do simulations, you can't spend 6 months or a year proving every theorem. You have to go forward. Sure you do. I mean, me too. I did my simulations. I used the algorithm, and I trusted my random number generator. But in many, many problems, we have sharp upper and lower bounds with constants, 2.5 and things like that. And then we know the shape of the cutoff. And so we work hard at trying to do it, but they're a handful of problems, and it's a lot of work. Each paper is a year's work, 6 months' work. And so, I mean, I can't beat anybody up, but there is a list of examples, and I don't know. I mean, I worry a lot about So I wrote a book which is also listed there called The Mathematics of Shuffling Cards, and in which we analyzed this overhand shuffle. How many of these does it take? And I said it was n squared log n. Well, it's between two constants, n squared log n. And when you put in the constants, n squared log n is around 10,000. And you put in the constants, in fact, the upper bound, I know, is 10 to the 39th, and the lower bound is 70. So I at least do put in the constants, and I'm embarrassed that we can't do it something sharper. But in many examples, we do have bounds that are usefully close together. 468 and 103 isn't so bad.
Yeah, that's good.
Okay. I don't know.
All right. Well, so if you don't have any more questions, so let's thank the speaker again. Thank you so much, Persi.